circuit due to noise in a receiver or optical amplifier noise. That means we will have such a signal pulse on or pulse, but actual signal pulse is not so clear shape as you expect, but noisy, fluctuate, and we, with some probability, they will have some probability of such a distribution probability. This is for Mach or 1 signal. This one will distribute. And zero level also distributes statistically. So this probability density depends on the statistics of noise sources responsible for current fluctuations. But almost all the cases, we assume that this noise distribution is so-called Gaussian distribution for easy of treatment, and actually true. So in a criteria, end-of-life BER should not be worse than 10 to the power of minus 12. This is actually specified in ITUT recommendations, 10 to the power of minus 12. Better than 10 to the power of minus 12. So such a requirement are described in some recommendations for SDH or OTN. You can see these recommendations. And this describes, again, the sampled value fluctuate from bit to bit around the average value I1 or I0. So this is a decision level, decision circuit level compared to the sampled value with the threshold value. That means that this is threshold level, and you decide this pulse is 1 or 0. This figure could be very clear. You can find this is 1 and this is 0. But really minor probability, this one could cross this line, so you can detect this is 0. So correct, incorrect decision. So actually transmitter send 1, but you detect it's 0, so error. So measurement of bit error rate. So the lower the bit error rate, the longer time to measure value. So this means that you have to take so much time to measure error rate. For example, if we use 10G system, 10G system means 10 gigabit pulse will be sent in 1 second. So you have 1 second. You have to have 1 second to measure at least one error. So that means one error at 1 second is 1 by 10 to the power minus 10. But if you measure minus 12, 10 to the power minus 12, you will take time at least 100 seconds, more than 1 minute. You have to watch your error detector more than 1 minute. And if you measure 10 to the power minus 15, 1 error per 28 hours, you have to watch the error detector 28 hours, more than 1 day. You have to detect. So long time. It takes long time if the quality of signal is better. Actually, actual optical system at the beginning of life could have so good error performance. So you can't detect error, but you want to know how is the quality of this transmission systems. But you can't measure the bit error rate better than this line. You have to wait for 1 year, 10 years, or 100 years to measure the very good performance of error, but it's nonsense. In this case, we will use actually difficult to verify the lower bit error performance. So we use, one idea is that we use the so-called statistical theory, so confidential level, 95. So this is often used in statistics. You know the 95% confidence you can estimate the real bit rate from such an equation using a so-called 95% confidence level theory. For example, 95% confidence level, that's 10 to the power minus 12 is required. This 3 times 10 to the power of 12 error-free bits are needed for 20 minutes at 2.5 G. Anyway, it's not so a good method to measure the error, just a statistical method. Then we will have a Q factor. You will see often the word Q factor in the if you have a transmission system or installed transmission system, the vendors will say the Q value of this system is 20 dB or so, and the end of life Q value is 15 dB or so. So Q parameters are often used to describe the quality of optical transmission systems recently. So what is the Q parameter? The Q factor corresponds to the signal to noise ratio at the decision circuit in voltage or current units. That means the Q described in such an equation. This means mu1 and mu0, the sigma 1, sigma 0, is just this statistical distribution of pattern 0 or pattern 1. So this pattern 1 will have average value mu1 and standard deviation sigma 1. And 0 pattern will have average value mu0 and standard deviation sigma 0. Yeah. So Q parameters is defined in this equation. This is, as you can see, this is just a mu1 minus mu0 is the signal level difference. So eye-opening like that. The sigma 1 plus sigma 0 means amount of noise in this system. And once you can know the Q parameter, you can calculate the bit error rate with this equation. This means the so-called error function. C means complementary. Do you know error function has a normal error function and a complementary error function? Almost the same. Same thing, but anyway, error function. Often used in a statistical or mathematical area. Yeah, you may know error function. And error function we have to use a calculated table of error function because error function given by the integration of this integration of Gauss type function. So you can't calculate this without using a computer or something, right? So simple approximation is error function is here. So you can use such equation if Q value is greater than 3. So the another approximation of the BRQ relation. So simple arithmetical calculation and no need to use error function table. For example, this equation minus Q squared divided by 0 like that is approximation is here. This approximation is good for a lower bit rate, but larger bit error rate regions, this line deviates from the original error function line. So this a bit complicated equation can better approximation of error function. So you may use this equation for describing the relationship between a Q and bit error rate, right? So this is the question. Just exercise Q question is the derivation of BER and the Q factor. It may be a good idea to do exercise by yourself why this Q and the BER relationship are made. And what you do is derive this relationship. BER is error function Q given by error function of Q, and the Q is given by this equation. And the error function defined in this form of function. Given information is just probability density function. This is the Gaussian distribution function, mu1 and sigma 1, mu 0, and sigma 0. The idea is very simple. The assumption one, first, both 1 and 0 bits are equally likely. So that means the total bit error rate is error 0 cent and 1 detected, or 1 cent but 0 was detected. So two kinds of error, sum of two kinds of error. You sent 1 but detect 0, or 0 cent but you detect 1. The total. And 1 and 0 have a Gaussian distribution as I described here, Gaussian distribution. The Gaussian, you may know Gaussian Gaussian distribution with standard deviation sigma and average value mu. Actually, Gaussian distribution means exponential minus mu, for example, x is a parameter, x minus mu divided sigma square e minus bracket x minus mu bracket square divided sigma square, like that, Gaussian distribution. And the total bit error can be minimum. Minimum means actually we set the decision level to be minimum to become the minimum bit error rate. So if we set the threshold level here, we will have so large bit error rate. Or here, we will have so large area of this integration area. So we will incur so large bit error. So the best point is just maybe around here. So this means that total bit error rate can be minimum when this PE 0 each or PE each, PE 1/0 equal P error 0/1. This is the condition of BER can be minimum. And the best threshold, here we describe D is can be threshold level minimized BER. So this condition, PE 1/0 equal PE 0/1 can be achieved by this decision level. Do you understand? So I'd like you to challenge this question during lunchtime or somewhere. I will show you the answer maybe later, but I'd like you to try this calculation and ask. And of course, you can ask me, and someone who will know about this question or about this contents can teach someone. Okay. Why I showed this program question is this is a very, very nice, good example to understand what is the Q parameters. Okay, so I recommend you try this question. Okay, and actually another. Okay, I will stop at this slide before the lunch. So Q factor measurement. So another question is how do you measure such a Q parameter? Okay, the Q factor is defined as the best decision level, as I said. And actually, this is the same figure, 1 level or 0 level, and the decision level will be set here, so the BER will be minimum. This is a bit really clear that decision level should be almost half of the level. If you set here many errors or here many errors, so best threshold should be around here. So we measure Q factor actually by changing the threshold level. Okay? So if we press decision level here, we will have so large bit error rate. And as increasing the level of threshold here, the bit error will decrease. And at the summer level, you can't measure bit error rate no longer because it will take so much time, 1 hour or 1 day or 1 year around here. So you will stop measurement. And again, you will change decision level so close to one level. So again, you will find a bit error rate, some countable bit error rate, and the bit error rate will increase as the decision level increase. So you can find such a graph and interpolate these plots. You can know the best threshold. This is just decision level, the voltage, or for example, 0 volt, 1 volt, and this is 0.5 volt. Anyway, best decision level can be found. And once decision level can be found, you can measure the Q value. You can also understand why such measurement can actually determine Q value if once you solve that question. Okay? Yeah, I will stop the morning session now for lunchtime, but any questions? Okay, so you can ask me after lunch or anytime concerning these topics in the morning session. Okay, thank you very much. So have a lunch, have a nice lunch. So we will start the rest of chapter 6. Have you tried this question? No? Anyway, I will give you the answer later, but now I will proceed chapter 6. Okay? So we will continue from this topic of forward error correction. So forward error correction, so-called FEC or FEC, are very important issue in optical communication systems. So forward error correction is not so new thing because already well established in wireless communication systems. And of course, an important way of improving the performance of large capacity long-haul optical transmission systems. The reason why optical communication systems have not used forward error correction maybe around 10 or 15 years ago, while a wireless system actually used forward error correction system. The reason is wireless system has a lower speed of maybe megabit or 10 mega or 100 megabit speed, but optical communication requires a higher speed of 2.5G or 10G, so signal processing speed cannot be available for such a gigabit region in the past. But recently, advent of high-speed IC technology, we can use forward error correction commonly in optical communication systems. So nowadays, forward error correction is an essential technique in optical communication systems. Actually, system design can accept a relatively large BER before decoding, around 10 to the power of -5 or 10 to the power of -6. And so significant relaxation of allowable optical parameters. So that means the construction of large capacity long-haul optical transmission systems in a cost-effective manner. So some application codes are specified with the mandatory use of forward error correction in some optical interface recommendations. So system BER is required to be met only after the error correction. So as I said, optical parameters are specified at a bit error rate not worse than 10 to the power of -12 as the FEC decoding output. That means we determine the bit error rate performance after the forward error correction. So that means we can accept such a no 1.8 10 to the power of -4. So very, very bad bit error can be acceptable if we use forward error correction. So forward error correction in optical systems are so effective in OSNR limited systems and dispersion limited systems. So in some cases, we can't improve any more bit error rate more than better than 10 to the power of -5 or -6 due to the such OSNR limitations or dispersion limitations. So reducing the out of the power is necessary if you are severely affected by nonlinear effects. So that leads OSNR decrease because we decrease the out of the power of the optical signal, the noise will increase, so OSNR will degrade. So G.709 OTN recommendation defines a stronger forward error correction for OTN. So actually, the coding gain provided by the FEC can be used to increase the maximum span length and or the number of spans resulting in extended reach. That means we can extend the repeater spacing from 50 kilometers to 80 kilometers, or even the whole length of the system. So in addition, the increase the number of DWDM channels which is limited by the out of the power of the amplifier. So there could be some limitation of optical amplifier output. So, however, we would like to increase the number of DWDM channels, so decreasing the power per channel, increasing the number of channels, because the total power is constant. So if you increase the number of channels, the power for each channel will decrease. And relax the component parameters like launched power, eye mask extinction ratio, noise figure, filter isolation. So those component parameters can be relaxed, and it leads lower component costs. And also another merit of forward error correction is enabler for transparent optical networks. As I described in the morning session, so-called OADIM or ROADMs or PXC networks in transparent optical networks introduce significant optical impairment because we will have optical switching device or optical DMAX devices in the network, in such kinds of networks. So if we use forward error correction in our optical path, that can cross more optical network elements that in such a network that can cross more optical network elements, forward error correction can improve the performance. So evolution from today's point-to-point links can be to migrate to transparent meshed optical networks with sufficient functionality. So of course, forward error correction is really a good technology to improve the performance, but we have to add any overhead for forward error correction. So forward error correction lowers bit error rate by a great deal for low overhead increase. But anyway, for example, Reed Solomon 255-239 forward error correction increased by 6 or 7% overhead. Of course, this RS 255-239 forward error correction can improve the bit error rate from 10 to the power -4 to the below the 10 to the power of -14. So the problem is increasing overhead for forward error correction. That increased rate is slightly reduce the overall coding gain. Reduce the overall coding gain. That means increase in the bandwidth. So I will describe later. And of course, some complex electronic circuits are necessary, so electronics cost. Of course, some forward direction or FEC use electrical max demand circuits, or line rate is increased. So we should note that there are some trade-off, possible trade-off between the performance and overhead in the forward error correction. So this figure is just simple definition of forward error correction. So usually we have such information bit. This is the original information bit, so K. And we will add this R bits that is called redundant bits to this information bits. So in total, we will have N bit length. N is, of course, K plus R. This R is so redundant bits. And this redundant bits can be used to detect and correct errors in this information bits. And in general, the code is called such a style, N comma K code. So I said RS comma RS bracket 255 comma 239 means 239 bits for information, and in total 255 bits. So this means 16 bits for redundancy. And the information word is not disturbed in any way in the encoder. That means that it should not be permitted to make some disturbance to this information bits due to the addition of redundant bits, of course. So this is a table for FEC terminology because forward error correction has a bit complicated configuration, so we should note the usage of terminology. So information bit, as I described, this is the original digital signal to be encoded by FEC before transmission. And parity bits, FEC parity bits, as I described in the previous figure, this means a redundant bit or byte generated by FEC coding. And code word means the information bit plus FEC parity bit. That is N in the previous figure, so total bit length. Code rate R means the ratio of the bit rate without FEC to bit rate with FEC. R is 1 if FEC is created inbound signal. So coding gain will be a reduction of Q values as specified BER, assuming wide version noise and theoretical reference receiver. Coding gain is just improvement of OSNR, SNR. So net coding gain is also a similar terminology, but this net coding gain considers the increase in noise due to the bandwidth expansion by the forward error correction. And the QP factor, Q factor corrected by the bandwidth expansion factor, so 1 by square root R. And BER, of course, in means BER before correction. For example, 10 to the power minus 4, and BER out is after correction, so better improved bit error rate. For example, 1 to the power minus 15 or so. BCH code, not used in actually OTN, but you will see often such a name, BCH code for forward error correction. This is just a name, both short-free Hokkien game code. I don't know. The most commonly used BCH code is the binary code. So RS code, this is the most famous one and actually used in OTN system as I described. This is so Reed-Solomon code, the most commonly used in the non-binary subclass of BCH code. So as I described, the forward error correction can be described in this style. code class BCH or RS, in this case RS 205, 55, 239, the number of information bit and the code word bits. So there is two kinds of forward error correction in general. One is in-band FEC, and the other is out-band FEC. The difference of in-band FEC or out-band FEC is just forward error correction parity bits are created in the inside of this information byte. In this case, maybe section overhead byte, or created outside of this information bit, like OTN. So we say, in this case, in-band FEC, and this type out-of-band FEC. So in the case of in-band FEC, parity bits are embedded in a previously unused part of the section overhead of SDH signal, I mean this place. So this type of FEC don't increase the bit rate of SDH because just use some of unused byte of section overhead. So, but in other words, only a limited number of FEC check information can be available, so limits the performance of forward error correction. So in general, in-band FEC cannot achieve so better performance, but do not increase or do not change any container size of such as SGH container. On the other hand, this OTN signal includes space for FEC bits. OTUK have a higher bit rate than the equivalent signal before the FEC is added OTUK, because this means this is the original size of a box or information, but we added this FEC bytes. So some increase in bit rate will be unnecessary. So a slightly increased line rate. So again, similar figures for configuration of FEC. So a read-Solomon decoder can correct up to 2 symbols that contain errors in a code word where 2t equals n minus k. As I said, this is 16 bits, so we can correct 8 bits per symbol per this container. And this read-Solomon code treats errors on a symbol basis. The symbol basis means one symbol contains 8 bits, so each 8 bits the error is corrected. So a symbol that contains all bits in error is as easy as detect and correct as a symbol that contains a single bit error. This means if this 8-bit container contains only one error, of course, this RS coding can correct the error. But also, if this container contains all the error, all the content is error. But even in such case, this RS coding can correct the error. Yeah. So RS code is particularly well suited to correcting burst errors, a series of bits in the code word received in error by the decoder. That means that in some cases, in optical communication systems, we will see a so-called burst error. Random error means that's randomly happened error. So, maybe a sparsely happened error. But burst error means with some reasons, like you touching a fiber or something like that, only instant, concentrated error generates. So in such case, even such burst errors, the RS coding can correct error. So this equation and this graph shows the RS 255239 forward error correction performance. So you don't remember such a complicated equation, but you should remember that this figure is based on this equation. And this equation is based on the probability of an uncorrected error, PUE. And this is a probability of a symbol error, PSE, and the code word length. Anyway, BER input and BER output is described in this equation, and this figure describes this equation. So you can see from this figure, this BER input, this scale is minus log BER. So this means the error rate of 10 to the power of minus 4, minus 5, 6, 7, 8, 9. And this vertical axis has so different scale of range, because this is error rate of 10 to the power of minus 20, minus 40, while this is just 4, 5, 6, 7, 8. So the difference in the scale. So as you can see, this without FEC means all exactly proportional to this BER input. BER output is exactly proportional to the BER input, of course without FEC. But if you employ forward error correction, this line steeply increase. Increase means a decrease in bit error rate. So drastically improved. For example, 10 to the power of minus 4 is here, but maybe around here, 10 to the power of minus 15 or so. So when you improve the bit rate a bit, even a bit small increase in bit error rates, in input bit error rate, but you can drastically improve the bit error rate output by forward error correction technique. So this is just a theoretical relationship between the line BER after FEC and before FEC. So this is the assumption with the assumption that errors occur independently from each other and that the decoder never fails. Of course, if the decoder fails to detect the error, you can check, you can correct the error. This is just a schematic figure of forward error correction in parallel processing. So this is because to enhance the immunity to burst errors, several RS code can be interleaved given the interleaving to depth n. That means as I described that RS coding is robust against so-called burst error, but we need more stronger immunity for burst error. We will use such interleaving. Interleaving means that's a risk hedge of something. If you are in line with 1, 2, 3, 4, 8 people and going to the same road, but if any accident happens, so all 8 people will be injured or died, but if 8 people will divide it to diverse way, even an accident happens, only 1 people will get injured or die, but any other 7 people can get alive. So this is just a risk hedge of the coding. So this single serial signal could be divided to so diverse route. So we can take a risk hedge of the bursting error. And so each elementary read-Solomon algorithm processes byte information and therefore works on 8 parallel data streams. The demultiplexers deliver 8 n data streams to the interleaved codes, and the multiplexer do the reverse operation. So they can do a risk hedge of error generation. Okay. So as I described, there is a so-called in-band and out-of-band FEC scheme as usual. So forward error correction in SDH and OTN. The in-band FEC are actually specified in a SDH system or in G.707. So the in-band FEC in SDH system use a triple error correcting binary BCH code, exactly a shortened BCH code. And this code can correct up to 3-bit errors in 4,359 bits code word. And the code word is an 8-bit interleaved signal stream from number 1 row of the STM and frame. And after 24-bit continuous errors in each row of an STM64 or 256 frame can be corrected. So currently, optical interface specifications for applications with in-band FEC are not provided recommendations concerned with optical interfaces. I mean that such kind of in-band FEC technology are rarely used in actual use, so we don't see so many times such kind of in-band FEC in SDH technology. Instead, we often see this out-of-band FEC specified for OTN system, G.709 described, that use the RS255239 scheme. So this is just a 16-byte interleaved FEC scheme, and that use 256 bytes for check information per ODU frame. So up to 8 bytes in the code word can be corrected, and the frame employs 16-byte interleaving, or so 1024 bits contained error can be corrected. So currently, optical interface specifications for applications with out-of-band FEC are provided. So this is, for example, 698.2 and 959.1. This application use OTN spec. So as I described in the table, in the previous table, there is two kinds of criteria, coding gain and net coding gain. What is the difference? So coding gain is a reduction of the signal to noise ratio at a reference bit error rate. That means BER reduced by the FEC is transformed in a dB value. That is, as I described in the morning session, as BER and the Q parameter, actually SNRs can be connected one-by-one relationship. So here we change parameter from BER to the SNR value. Because we can say SNR 1 dB or 2 dB is easy to describe system performance, but it's very difficult to, if you say 10 to the power of -9 to 10 to the power of -6 or something like that, very, very complicated description if we say in bit error rate. So we say in dB scale, that's SNR improvement. So this kind of parameter is directly applicable to an in-band FEC because it needs an increase of the bit rate nor the noise at the decision circuit due to receiver bandwidth expansion. So this coding gain can be directly used in-band FEC system like SDH, but we also have another parameter, net coding gain and net coding gain. This is also established for out-of-band forward error correction. The performance of an out-of-band FEC can be characterized better by a modified coding gain parameter, that is net coding gain. So this means the bandwidth expansion for these out-of-band FEC schemes is associated with increased noise in the receiver because we increase the bandwidth. Bandwidth increase means increase in the noise in the receiver. So system gain optical SNR limited systems can be estimated accurately. Okay? The reduction of the electrical signal to noise ratio reflects the allowable reduction of OSNR. So for comparison of high efficiency FEC schemes with different code rates used in long-haul systems, the NCG parameter is a good measure. Roughly speaking, this is just net coding gain. So you may understand easily the name net coding gain. Like, for example, you can buy this bottle of water $1 in Ruhengeri, and if you take this bottle to Kigali, you can sell this $2. So the gain is $1, but if you have to pay a tax of $0.2, if you buy this bottle, net profit or your profit is 0.8. So similar thing, yeah. Your net profit or just nominal gain, profit. This is just simply coding gain is nominal gain, but actually your net gain is net coding gain. Yeah? So this is just to describe the bit ER improvement by forward error correction. This is just a Q parameter, so-called SNR. So under some SNR, we have such a bit error rate versus Q relationship. As you have seen in the morning session, we will have Q and error rate relationship. This is. Sorry, this curve is OTUK effect disabled, this line. And if we adopt this forward error correcting, so we can get this curve. So then this line measured at the bit error rate of 10 to the power of minus 12. We say this is coding again. From here, crossing point with minus 10 to the power of minus 12 here from here. But actually, if we consider the increase of bandwidth, that leads to the reduce of some SNR reduction. So we have to take the point from here to here. So we can get a net coding gain is a bit reduced value from the so-called coding gain. Right? And this relation is described in here. This is just a table corresponding to the previous figure and performance of a standard FEC. As I described, the inbound FEC, BCH type FEC is used in SDH, and out of band FEC is used in OTN, so-called RS255239. So the bit error rate for output bit error rate of 10 to the power of minus 12 as described in recommendation, any application codes, 10 to the power of minus 12. So this inbound FEC scheme requires a bit error rate 2.9 cross 10 to the power of minus 6, but this out-of-band FEC can reduce the error rate 1.8 cross 10 to the power of minus 4. This means this out-of-band FEC scheme is better performance than the inbound FEC. So look at this coding gain. Coding gain is 3.8 dB, and OTN actually better coding gain 5.9 dB. Yeah. But if we compare the net coding gain, so coding gain and net coding gain is the same in inbound forward error correction, 3.8 and 3.8. This is because, as I described, the inbound forward error correction don't increase the bandwidth, so don't increase the noise. But this out-of-band FEC schemes, the net coding gain slightly decreased. You can see from 5.9 to 5.6. This means 0.3 dB is due to the degradation of led by the increase of signal bandwidth. Yeah? Same as the tax. To do something, you have to pay tax, okay? And actually, code rate is, of course, in band is the same bandwidth over 1, and out of band forward error correction is 239 by 255. This is the same, just same as 255, 239 coding. Yes, actually, I have described about so-called standard FEC. Standard FEC is used for interface, standardized interface like OTN or SDH. But we don't need to adopt such a standard FEC if we don't use compatibility between interoperability between the vendors or something. We can use any forward error correction schemes freely. So this is some example of non-standard forward error correction. So there could be so many various ways of FEC scheme, enhanced or proprietary FEC schemes are explicitly allowed and widely used actually. So forward error correction performance can be evaluated by that net coding gain or robustness against the burst of error or latency and cost. This table shows the example of currently used non-standard forward error correction schemes. So actually, bandwidth is with increase in bandwidth is 5%. NCG gain is 8.6. As we see, we saw the previous table that standard forward error correction can only improve the performance 5.6 dB or so, but non-standard forward error correction, one of non-standard forward error correction schemes, we can get 8.6 dB gain, really high gain. And if we increase the bit rate to 7, 10, 15, 20%, so really huge number of increase in bandwidth, but we can get a higher net coding gain, 9 dB or 10 dB. So it depends on your requirements that if you want to have a so stronger forward correction, you may adopt such kind of non-standard forward error correction. Actually, this figure shows this fact, so-called progress in non-standard forward error correction. So BTC means a block turbo coding. Soft decision is also a new technology for forward error correction. And new forward error correction available higher speed interface like 100G is. So this is just uncoded bit error rate, SNL or Q value relationships. But first generation means this RS25239, just this performance. After that, around 2000, RSBCH can achieve 719 dB improvement. And now a bit older, but now 2003, block turbo coding can improve more than 10 dB net coding. This is third generation. Of course, we have a limitation for forward error correction. That is called the Shannon limit. Some of you have heard such a name, Shannon limitation, was Shannon's theory in communication systems technology. So this is called Shannon limit. So we can't improve over this line, but currently really closely approaching forward error correction technique are developed. So forward error correction manipulates optical original signal bits and add parity bits and manipulates so many complex way. So our concern is that increase in latency by the such a manipulation of electrical circuit. Before the discussing for the elaboration, we should remember that propagation time in fiber, this is definitely, we cannot reduce because the speed of light in a fiber can be fixed. You can't change. You can't reduce the speed of light in a fiber. Okay? So as you can see in the air, the light can propagate in a second 7.5 times around the globe. Yeah, 7 times and a half. That means 300,000 kilometers per hour in speed. Okay, I don't remember anyway. So how about the speed in the speed of the light in a fiber? Can anyone answer? 8? 8 means what? 10 to the 12 by 80. It's in the air. In the air. Light speed in the air. My question is light speed in the optical fiber. Do you see? A very, very, very simple question. You don't need to think so hard. No problem. Okay? Can anyone answer the question? The light speed in the air is 3 cross 10 to the power of 8 meter per second, right? And in the fiber? Same? Does anyone? Same? Your answer is the same? Sometimes people forget a very simple thing. Unfortunately, who answered the same is incorrect answer. Why? Do you understand? Does anyone have a right answer? Oh, this is, sorry. I don't understand, but any reason that this is incorrect. This is in the air. Okay, sorry. Maybe. Forget this number. Okay. So right answer is 2 by 10 to the power of 8 meters per second. 2. Why? So the refractive index of the air is almost 1, okay? Same as the vacuum 1. But what is the refractive index of glass or fiber? Do you know? Refractive index of the glass is 1.5. That means the light speed will slow down by this refractive index. So the actual speed of the light in the fiber is 2 cross 10 to the power of 8, 2 cross 10 to the power of 8 meters per second, not 3. 2 is right, okay? So you have to say, when you discuss about the delay in the fiber, you have to use the speed of light 2, not 3, okay? For example, 10,000 kilometers propagation, maybe trans-Pacific from Japan to USA, almost about 10,000 kilometers. The light delay latency is about 50 milliseconds, because the light speed of the light is 2 cross 10 to the power of 8 meters per second, not 3. Okay. Anyway, I'd like to explain here is just we can't reduce the latency of the propagation time of the light, but we will also have latency by the electronic circuits in the optical transmission equipment. So problematic thing is we will also have latency in forward error correction circuits, but actually Reed-Solomon coding don't add so large latency, maybe less than 1 millisecond. But some forward error correction chips, in particular used in one system or so, have longer latencies. And some RAN applications, smaller block sizes are preferable for minimized buffer size. Okay. I will stop here about the forward error correction discussion. So do you have any questions? It's okay. Oh, generic question. So shall we continue? So another issue in the chapter 6 is so-called compatibility in optical interfaces. So this is that just as I described, the transverse compatibility. This situation is this vendor A and the vendor B, that is different vendors.